Welcome to the Eulerian Integrals again, and today we need to talk about the Euler's integral of the second kind, which is known under the famous name the gamma function. This name was given by Legendre, and also I will derive very useful and important the Euler-Gauss formula, which is another representation of the gamma function. The gamma function is probably the most important non-elementary function in all of the mathematics, the natural sciences, and of course the probability and statistics. You can Google it, you can see so many different versions of the gamma function. They all look different, but that is the same function. Many scientists were modifying it, blending it in with different formulas while bringing different properties, and they came out to their versions of the gamma function. First of all, how did gamma function come into our life? That is the 16th, the 17th, the 18th century, when many scientists were fascinated with the idea of expanding the domain of the factorial function onto the set of the real numbers. They wanted to come up with the smooth, continuous line which would interpolate the factorial trend. Why the continuous smooth line? Because once we have it, we can involve the calculus tool, the derivative, which will open the doors to many properties of this trend. For example, the rate of change, the growth, and other useful indicators. Euler the Great was also digesting this information while using the previously established statements, discoveries. In 1729, 1730s, and sometime 1738, he published absolutely amazing result. He evaluated the factorial as the infinite product, kind of the discrete structure, and as this integral of this log, kind of continuous structure, integral from 0 to 1, this log s for n ds minus, it converges for n more than 0. He exactly proved that. He derived those important formulas. That was kind of breakthrough. And later on, Legendre, he just slightly modified this integral formula while introducing this transformation. No problem. Continuous, one-to-one, so no ambiguities. You can just introduce it. He just wanted to get an integral from 0 to infinity, kind of cumulative probability-like structure. So it's useful for the probability. So s changes from 0 to 1, consequently, new variable t will change from infinity to 0. You all know that, simple calculus. S is equal to e power minus t, so ds will be e minus t dt with the minus sign up front. T will change from infinity to 0, so if you flip from 0 to infinity, will be no minus, and tn is that. So this way, you will get your n factorial represented as this improper integral from 0 to infinity. That's actually Euler's integral also. And consequently, n minus 1 factorial is equal to the same integral where t is just being raised to the power of n minus 1. The rest is the same. And Legendre just called it the gamma of n, the gamma function, the third letter of the Greek alphabet, the capital letter of gamma. As you can see, it's a function of one variable, of one parameter. So finally, the gamma of a is equal to this improper integral from 0 to infinity, x power a minus 1 reduced by 1, e minus x dx. And this integral, improper integral formula is probably one of the most, if not the most commonly used gamma formula. Why? Because it's very practical for the probability and statistics. Because we know in the probability and statistics, the exponential distribution is one of the most important distributions there. And what's very important for the distribution? To know its statistical moments. The average, the first moment, the variance, the second moment, the excess, the third moment, the kurtosis, the fourth moment, and so on and so on. So if you want to calculate the average, you take your random variable, weighted by the exponential PDF, the probability distribution function, e minus x, and you integrate it within the whole range of the random variable from 0 to infinity. This is how you calculate your expectation, the average of the random variable. The variance x will be squared, and so on. For each statistical moment, here we'll have different powers of x weighted by the PDF, by the exponential distribution. That's why this is very practical formula of the gamma function, very useful for the probability and statistics. This improper integral converges for all the a values more than 0. I've discussed it in my previous, the beta function clip. We also proved that in the calculus and analysis, improper integral will converge for positive a values. And today, we'll follow Gauss, we'll follow this red arrow, and we will derive another very useful, important, the Euler-Gauss formula, which is another representation of the gamma function. So, following Gauss, we'll set a new transformation. X is equal to ln 1 over z. Now, this is what it makes to be a great mathematician. Why ln 1 over z? First of all, can we use this transformation? Yes, perfectly fine, because x changes from 0 to infinity. Ln is a continuous one-to-one function, so there will be no ambiguities. I can map each x from here uniquely to a log function, changes from minus infinity to plus infinity. Now, why ln? Why not another function? Now, let's recall my clip, the special limits of calculus, all 5, where I discussed the special wonderful limits. One of them was the exponential limit, zx minus 1x equals 0 is equal to ln z. And I said there is very useful modification of that limit when we introduce a new variable x is equal to 1 over n while switching to a natural domain. It goes to 0 and will go to plus infinity in this case. And x is 1 over n and goes up top, so will be no fraction, and the nth root of z minus 1 and goes to plus infinity, natural, plus infinity now, and it's the same ln z. So this ln will bring us this discrete natural numbers structure into this gamma function. Now, why 1 over z? Why not just z? Later on, we will see that 1 over z will bring us to the beta function. If it's just ln z, it will not bring us to the beta function, so it won't give us much. So that was a smart, brave move of the genius. Predict those steps. So introduce a new variable, x changes from 0 to infinity, new z will change easy from 1 to 0, easy. You know, easy. x0, ln has to be 1, so z has to be 1, x infinity, ln is a rising function, so 1 over z also goes to infinity, which means z goes to 0. Now dx is minus dz over z. So 1 over that, 1 over 1 over z, dz, multiplied the chain rule by z minus 1, derivative is minus over z squared. So z over z squared is just 1 over z with the minus of e dz. That's my dx. Now let's plug everything into my gamma function, and finally we can write it as the integral. So instead of x, we have ln 1 over z power a minus 1 e minus, instead of x, ln 1 over z. Instead of dx, I have 1 over z dz. Yes? And this minus, let's say, up front of the integral, and my limits are from 1 to 0. And that's simple modifications. So I can flip my limits, no minus sign, so it'll be from 0 to 1, no minus, ln 1 over z power a minus 1. What is that? It's a simple, basic logarithmic formula. E to the power of ln, just collapse it. Yeah, you all know that. So it's just 1 over z raised to the power minus 1. So it's just z. Z over z. Reduce the fraction, dz. So this is what we have. It just comes to this integral from 0 to 1. Now, ln this is what I said, very useful modification of my exponential wonderful special limit. I will try to bring it under the integral, this natural domain. So which is equal to the integral from 0 to 1. And again, that's ln z. Here we have ln 1 over z. You remember, that's ln z power minus 1. So minus 1 comes up front of ln. So ln z with the minus sign. This is actually ln z with the minus sign up front. So we'll just bring this limit with the minus sign, because that's ln z is equal to that limit. And here I have ln z with the minus sign, so the limit with the minus sign, which means that I can bring this minus sign under the limit while flipping this difference. So we'll just the limit under the integral n, and here 1 minus z to the power 1 minus n. Everything to the power of a minus 1 dz. I hope that's clear. I just brought this limit under the integral with the minus sign because it's ln 1 over z. Again, that's z power minus 1 minus cos of front, the property, the basic property of the logarithm. So minus in front of the limit, bring it in here while flipping 1 minus z power. Now, important step, flipping the limit integral, in which case we can do that. Recall very important theorem. Note, remark, that the function n 1 minus z power 1 over n is first monotonic, increasing, it's easy to show that using calculus tools. Just integrate it, look at the, just differentiate it, look at the derivative, we'll have positive sign. It's monotonic increasing to its limit. Which is equal to ln 1 over z when n goes to infinity. Yeah, when n goes to infinity. And second, it converges to its limit uniformly. It converges to its limit uniformly. So those two important conditions, monotonic and uniform. And we know there is a theorem we discussed in analysis. In this case, we can flip the sign of integral and the limit. So know that the function is monotonic, increasing to its limit when x goes to infinity, and the convention is so we can flip integral and the limit. We can flip them. So finally, we have, in this case, our gamma function is equal to the limit now. So I'm flipping the limit and the integral, n to the power a minus 1. The integration is done over the domain of the z variable, so n to the power of a, kind of a constant in this case for the integral, so you can pull it up front of the integral. So it will be n power a minus 1 when n goes to infinity. N goes to infinity, of course. N goes to infinity. 1 minus z. So here under the integral from 0 to 1, we have 1 minus z power 1 minus n raised to the power a minus 1 dz. z. I hope that's clear. I just pulled n power a minus 1 up front of the integral. I flipped the limit, sign of the limit and the integral, and as outside of the integral. Now this looks like kind of a beta function structure. This is what we'll do. We'll introduce a new variable, say let z power 1 minus n is equal to y. Then y power n is equal to z. Yes, then my dz, I need to calculate my dz, will be just equal to n y n minus 1 dy. And again, I'm switching to a new variable y because it brings me to the beta function. And new limits of integration will actually be the same from 0 to 1. You can see when z changes from 0 to 1, y also changes from 0 to 1. It's easy to see that z0, n is not 0, has to be 0. z1 has to be 1. Easy. So it's equal to the limit n goes to infinity. Now, one integral from 0 to 1, 1 minus z, 1 over n, a minus 1. So it's 1 minus y power a minus 1 dz is y n minus 1 dy. Now this n also comes up front of the integral, and I will combine that with this n a minus 1 by n a minus 1 plus 1. So just n power of a up front. This is what we have here. What is that? That is exactly my beta function of two variables and a. I discussed that in my previous clip. So it's equal to, it's finally, hence, so this is what we have. The gamma function is equal to, let me just write it, it's the limit, n goes to infinity, n power of a by the beta function n a. And now let me just expand it, n goes to infinity, n a. Extend the beta function. It's 1 by 2 by 3 up to n minus 1, as I derived it this way in my previous clip, a plus 1 up to a plus n minus 1. And it's equal to, since n goes to infinity, I can just go up to, let's say, n. It doesn't matter. We'll just, for the convenience, I'll just rewrite it as the limit n goes to infinity, n power of a 1, 2, 3 up to n over a by a plus 1 up to a plus n. So it's finally equal to the limit n goes to infinity, n power of a fraction. Here I have n factorial over a by a plus 1 up to a plus n. And we just received this wonderful result, this wonderful formula. Gauss came up to this formula of the gamma function. It has kind of computational nature. So instead of just calculating this improper integral, sometimes it's difficult. Easier would be just use this computational approach. All products, powers, and just the limit. So it's a nice modification. It's a nice version, actually a very useful version of the gamma function. I hope that's clear and interesting. This is what I would like to tell. I just called Euler the other day. I talked to him. I said, "Your highest knowledgeness Euler." I just came across through the Russian mathematical literature, through the German mathematical literature, through the mathematical literature of some Asian countries, and they all call this formula the Euler-Gauss formula. And for some reason, in the English-speaking world, English language books, they use this formula. They mention that it was derived by Gauss, by Euler, but they never actually call it the Euler-Gauss formula. You know what he told me? He told me, "Could you please call Gauss, talk to him, tell him the same thing." The next day I called Gauss, I told him the same thing, and he told me, "It's up to you. If you want, you can declare that." So this is what I would like to officially declare. This formula has a name. It is called a wonderful, the Euler-Gauss formula. So this is the Euler-Gauss formula. Two mathematical giants ever lived on Earth, the Euler and Gauss modified gamma function. They came up to this version of it. This formula has a name. This is the Euler-Gauss formula. As you can see, when you Google gamma function, you may discover some other formulas of the gamma function. You can also, if you take, let's say, the three piglets formula, bring it in here, mix it, blend it in, and you may be able to come up with your own version of the gamma function. No problem, as long as it's correct. In my next clip, I will discuss an infinite product of the gamma function. We will see how Euler the Great modified it, and he came down to the EGF, the Euler-Gauss formula, which means it's the evidence of another version of the gamma function. So this way, the two-star formula and the one-star formula actually represent the same thing. I hope that was clear, interesting, informative, useful. I also hope you enjoyed that. Thank you very much. I will see you soon in my next clip, again, where I will discuss the infinite product version of the gamma formula. Thank you very much again. Talk to you soon. Bye-bye.